So you are welcome to today's session. I want to start by asking if there's any question concerning what you have done before. So any question? Yeah, so let's, we stop at the chi-square, basic chi-square, yet corrected, Fisher exact test, and a likelihood ratio chi-square. Those were the things we did yesterday. And if you remember, what I have on the screen is actually the output of what we had yesterday, the output of that analysis. And you will see that if you have any, if you say what we calculated with hand, you say exactly the same thing the SPSS was able to run for us. And you remember that the degree of freedom is 1 because that scenario is 2 by 2 table. That's the smallest degree of freedom you can observe. And that is where contingency table you can have. So there's something I said I will quickly explain. I can't remember, maybe the process. If I remember, I will go back. When we were closing yesterday, I said something, I will see, come and explain it. Yeah, let's move to today's business. Let's quickly look at chi-square for trend. No, chi-square for trend. I hope you can see my screen. If somebody can see, let me know. Can you see the screen?
Yes, I can see your screen.
Yes, I can see your screen.
Okay, we want to look at chi-square for trend. So this chi-square for trend, if you remember, is the last output you saw yesterday when we were running Pearson chi-square. Of course, there after Pearson, you see the Yates corrected. And the Yates corrected is because it is 2 by 2 table. If it is not 2 by 2 table, that is not 4 cells, you will see Yates corrected. It will not even come out. But you see the next after Yates corrected, you will see the likelihood ratio chi-square, and whether 2 by 2 or 1 or more than 2 by 2, you will see that after Pearson, you see likelihood ratio chi-square. You see Fisher exact. Also, if you have clicked the exact before, and the last one you saw there was, you see linear by linear. So that linear by linear is the chi-square for trend. There is not all the situation that is applicable. So, you know, computer is garbage, you program it. So whenever it's applicable, it brings it. If it's not applicable, you neglect whatever it brings to you. Now, this chi-square for trend is for assessing whether a binary variable varies linearly through the level of an ordinal variable. Can you see now? There are 2 things I want to note. A binary outcome. A binary variable means that this variable, there are 2 possible outcomes, either yes or no, male or female, whatever. So that outcome, 2 possible values you can have. So maybe good knowledge, good poor, person immunized, yes or no. Think of many things. Is it diabetic, yes or no? Think of any outcome that is only 2 possible values. That is binary outcome, binary variable. Then linearly, if it's very linearly, 2 levels of an ordinal variable. So the exposure must be ordinal. When we say ordinal, the outcome is 2 categories, but the exposure must be ordinal. When we say ordinal, it means that there is hierarchy, like age group now. You know, a group, you know, less than 20, 10 to 29, 10 to 39, 40 to 49, all those is ordinal. If you have level of education, is ordinal. If you have socioeconomic class, is ordinal. Level of profession, occupation is ordinal. You know, the occupation that you just go and civil servant, this one, no, it's not the right way to do occupation. There's what we call register general classification, where it is in hierarchy. So whenever you have any exposure variable that is hierarchical, that is ordinal, and your outcome is 2 possible outcomes, then the chi-square for trend is good for you. In fact, it's the best. Sometimes when you have ordinal exposure variable and you just do basic chi-square, it doesn't have meaning because you want to see along the ladder How does it vary? Does it change along the ladder? Like for example, you are testing something now, employment status among different level of education. It's good. It's not good to just say, it's highest among the secondary school level. But you want to see, does it increase as the level of education increase, or does it decrease as the level of education decrease? Because that's the one that can make meaning in that situation, the trend. And that is what this chi-square for trend is doing. The null hypothesis is that the value of the outcome variable is the same for all the of the ordinary value. Of course, null hypothesis says there is no association, there's no change. All of them, that is, the outcome variable is the same for all the different categories. That's what the null hypothesis will say. But alternative hypothesis will say, no, it's not the same. In fact, it goes with the trend. It's either decreases along the trend or increases along the trend. Now, you see, for you to be able to calculate it, sometimes it's just some of these calculations also can be cumbersome, but just for you to, why I'm making this effort is for you to understand some logic behind it. So once you understand the logic, all you need to know is to know how to use your software to run the analysis and know how to interpret. So you cannot be reinventing it. Now, look at this table. You see, look at level 1, level 2, level 3, level 4, like that. This just an let me just move to the next one because I prefer, let me show you the same table that show example. It makes more sense. Look at level of education. It's an ordinary variable. It's the exposure variable. You remember, you say always put your exposure variable along the horizontal. You can see now the level of education, no formal, primary, secondary, tertiary. They are the one along the rows, horizontal along the rows. Why the outcome variable? Outcome variable is the employed. Yes or no? It's along the column. So now the exposure variable is ordinal. Why the outcome variable is dichotomous, is binomial, is two categories. It's binary. So another way of saying binary is dichotomous, two, or binomial also. So you see that yes, no, employee, yes or no. You can now see, you'll be able to see the percentage. You can see the total now. For the no formal, 5 employed, 10 non-employed, the total is 15. For primary education, 35 employed, 50 non-employed, the total is 85. The secondary, 80 employed, 45 non-employed, total is 125. Tertiary, 65 employed, 10 non-employed, the total is 75. Now, the absolute value will not make meaning, just like what we saw yesterday when you were trying to judge if which sex group category is more employed. You say that female, because you see that we have 95 female employed compared with 90 female. But you've forgotten that 95 out of many, out of 170, is smaller than 90 out of 130. So that was what made, when you analyze it like that, you'll be able to tell that averagely the male are more employed than the female. It's not the absolute figure, but you transfer it to percentage. Now, the absolute value we give you now, you don't make meaning until you put the percentage. Okay, for this no formal education, what proportion were employed? 33.3%. That is, out of 15, 5 were employed. For the primary education, out of 85, 35 were employed. The percentage is 41.2. Secondary education, out of 125, 80 were employed. The percentage is 64. And tertiary education, out of 75, 65 were employed. The percentage is 86.7. If you didn't use it, you may be forced to say that, oh, secondary education, they are more employed because we have 80 of them. If you say out of 185 that are employed, 5 have for no formal education, 35 are primary, 65 as tertiary, and 80 as secondary. You give the impression, those who are secondary, they are the ones that flood the place. So, whereas out of what you know their denominator, the majority are in that category. So you see that from that, you'll be able to know that the tertiary education people are more employed because they are fewer than in total number, they are fewer than the secondary. In that situation, you see that if you put the number employed over the total in each category, you know that the tertiary education are the most employed, followed by secondary, then followed by primary, then no formal education. We want to see, of course, you can see the trend. Sometimes it's not always like that. As you can see, the percentage increases. You may see that one shot, or maybe that second itself, the percentage is higher than tertiary. It may happen, but it doesn't mean that there's no trend. If there's a break somewhere, doesn't mean that's it. So for you to be able to decide if there's still trend, you have to put it test. Even by looking at it now, you may see things a trend. The trend may not be much, and you put it to test, it may not show significance. So that is the essence of that chi-square for trend. So this table now, you are just explaining, show the employment status among people of different level of education. I won't say that the employment status very linearly along it. So this one is just to give a theoretical something better. To me, something that you will begin to see, begin to confuse you. But so sometimes when you are making your presentation, you want to have some level of academic account there. But they don't actually need it because I prefer explaining it with example. And when you now go back now, it makes sense. In this level, CCC you are seeing now is just the number, the yes number, the no number. This is event. Event here, employ. The example is employ. Yes, no. So the what we are just then this ordinary exposure mean is this level of education, is it level, is economic class. Think of anything, you see age group. So anything that has hierarchy will be the one, level 1, level 2, level 3. So you see the total now. The total will look at it now. You now see the score. There's a score, the trend score. And that is where we are going. So how do you calculate it? And if you don't even know how to calculate it, if you just even understand what I just explained, you know how to run it, it gives you a result. And that's what we just do here. We compute here. First, assign a numerical score across the categories of ordinary variable from 1 for the lowest serially to the highest. So look at it now. The same something I now put, okay, 1, 2. This score is just a code. You start from the lowest, you put it 1, 2, 3, 4. If they are up to 5 categories, now put up to 5. It's just arbitrary code. When you now put it, calculate the mean score for yes, no, and overall by multiplying the allotted score for each category by the frequency in the category. So what it just does is to multiply, look at this category 1, which is normal, no formal education. So you now say, okay, the score there, which is still will be 1, the score is there is 1, times 5, the frequency is 5, plus 2 times, can you see the T1 for 2 times 80, 35 rather, that's for the primary, times 3 times 80 for the secondary, 4 times this, it gives you this. So T2 will be 1 times 15, that's the total. This one, the first T1 is for the total. And for the yes, rather, the T2 is for the total. 1 times 15 plus 2 times 85 plus 3 times 125 plus 4 times 75. Then this T3, 1 times 15 plus 4 times 84. If you follow it now, you see 4 times 85, 9 times 123 plus what do we have here? 85, then 125. If you look at it now, are we following? Are we following? No, this one you are using square. Okay, the third line T3, you are using the square instead of using it. You are squaring the score before you put it. Okay. Yes, sir. Now this 1 square is 1, 2 square is 4, 3 square is 9, 4 square is. Can you see now? Are we together? If you follow it, if you look at it, okay, maybe I will have started with the formula. The formula for the trend is T1 minus CT2 over N bracket, everything in another bracket square all over V. Now, if you, let me come here, you see what it means. That formula T means sigma of the C, which is the yes, your yes times the score. T2 means the sigma of your total n times the score. T3 is the sigma of m times square of the score. And V is CD n T3 minus this over n square n minus 1. Look a little bit, but if you follow it, it will just give you the answer. So when you do that, you just put all those jargon and give you this. So now the chi-square, the degree of freedom is usually 1 for the trend is usually 1. So imagine for the degree of freedom of 1, you are having chi-square of 39. It's very high. You know that's significant because for the degree of freedom of 1, the chi-square, the critical value for chi-square is 3.84. So this one is far above the critical value for the degree of freedom 1. So you can now see that the trend is there. That's just the summary. And let us run it. This is the step you want to use to run it. Somebody should, it's very simple. Just like any other cross tabulation you do. Let somebody share with us now. These are the steps for running it. Let somebody share with us so that share the same file of yesterday's socio-economic file. Dr. Lamingo, welcome. Let somebody share. Who will share so that we can use to run this? Because inside the same file yesterday, you have the level of education and the employment status. We do use the employment status together with sex. So when you compare, when you look at sex and employment status, you know that exposure is sex, employment status is the outcome. The same thing also, when you look at relationship between level of education and employment status, you know that level of education will be an exposure, employment status will be outcome. Who is sharing? Nobody can share here. The same file of yesterday, all your this thing, bring it out.
I wanted to share, but on my screen.
Okay, sorry.
Hello, you need to enable for us to share.
I have enabled, sorry, I've enabled now. Sorry for that. It's coming. Ben is here. It's coming. It dropped again. I don't want to do the share. The thing just dropped. Okay, it has opened. Why is he doing that?
It's for me. I'm trying to share.
No, it's already shared. I was thinking it was Ben that was sharing. Okay.
No, I was the one.
Yeah,
I was the one.
I tried sharing, but I think.
Okay, then maybe network or what? Okay, no problem. Now you will see that in this we have the employment status and education. All you need to go, just go to. We are not seeing all your icon. What happened? We are not seeing. Nothing is blocking the icon. The analysis icon. Analyze. Go to analyze. We are not seeing it. Go to analyze. Just go there. You cannot see, but just if you can see your own analyze, just go. You cannot see your own also, eh? It's like you are not seeing it also. Oh, should I share from there? Dr. Lamingo, why are you not sharing? You have not shared since yesterday. Dr. Lamingo, you have to.
Yes, sir. Let me share.
Okay. Okay, Ben has shared now. Okay. He's going out. It's good. You can share, Dr. Lamingo. The Ben's network is not going. Maybe where he is. Maybe he's in a remote place. It's the network.
My location. I've changed my location.
Okay. I can only follow in the life. Yes, okay.
I've shared again. I'm done. Yes.
Yeah, I've seen it. Okay, you show now. Go to analyze. Cross tab. No anything about chi-square. Except one we are going to do later. You see that? Cross tab. Is your hand shaking? No, you have to first of all. Yes. So your exposure is level of education. You move it to the row. Your outcome is employed. Employed, yes or no? So you don't even need those exact. You don't need it. Go to chi-statistic, click on chi-square. Because if you don't click on chi-square, it will not do it for you. Chi-square. Yes. Come to continue. So you may want to go to cells. Remove that. No, don't put that. It's better leave it. You don't need it. Even that yesterday, we don't to be putting expected. It's just for me to explain. When you are running your this thing, you don't need it because you are not writing the expected half. So you don't even need to click on it. So click on row. Continue. Okay. Stop sharing and share the output. And stop and now share the result. Okay. Share the output. Okay, that's great. You will see, scroll, if you look at all those percentage we put, you see that. You know, me, I've already run it and put the percentage, or maybe you can use hand to calculate for illustration. Normally in your data, if you don't put that the right percentage there, you get problem. You have to know that you have to put row percentage. Scroll down. Scroll down. Let's see the statistic. Can you see the Pearson chi-square? You are not looking for Pearson chi-square, but it will show you. We give it to you. So you see Pearson chi-square, you see likelihood ratio. Can you see? Because this one is more than, it's not 2 by 2 now. It's 2 by many tables, so it's not 4 sets. That's why you don't see yet corrected chi-square. Then you see likelihood ratio chi-square. You now see linear by linear association. That is the chi-square for trend. And you look at it, no matter how many level of the category of exposure, the degree of freedom is usually 1. You will see that you see 39.185. That was what we calculated with hand. And can you see the p-value in the SPSS? Significant the p-value. That's the language they use. Those significant level is different from p-value that. That's what they use in their software. You know, they are business people. They are not necessarily statisticians. They are business people that are programmers. Their own is just to get a statistician to help them give the formula, how it works, the logic, and they will do the programming. So they use, instead of p-value, they put significant. That's when she's sick like that. It means SIG. It means p-value. That's their own p-value. So the p-value now is less than 0.01 when it is small. So if you continue now, it may be 0.00009. No, you cannot be writing to those decimal places. That's why when you see 0.0, it may not necessarily mean 0. It may mean that it's extremely small. And that's what people do when they see that, is that they now say, okay, it is less than 0.001. Now, I want you to rerun it now. It will not change anything. I want you to rerun it and now put the column percentage and come and see how you can be misled. Well, go and rerun it. Go to analyze. Go to go back just to that same place. Cross tab. Just go and change the percentage to column rather than row. If you show both row and column, percentage, it will cross tab. You have put it's the way you have to first of all enter. You put your enter through the split horizontally, go to frequency first. It's only that you will not click on frequency. If you do that, it will not take you out. But when you are bringing, from there you come. Just go to cells. Go to column percentage, click on the column. If you click both, it will show you, but it will be too much. That's why I don't remove the row so that it won't be, you can pack the place with many percentages. You may be confused. Click continue and OK. You see down. Oh, you see that if you look at the same place now, other years now, you'll be seeing like 2.7, 80.9, 43.2, 35.1. It's giving impression that secondary is higher. And what it's just doing is that it just because it's column percentage, the percentage is along the column, along the employed, along the outcome. It's telling you out of 185 people that are employed, the highest number is in secondary school, is 43.2, well, followed by tertiary, which is 35.1, followed by primary, 18.9. Is the least is secondary, is no formal education. That's what it means. But it has not, it's a wrong interpretation if you go and use that, because we are not interested in what you are in. If you are looking at association, we are not interested in how out of many people that have the hardcore, how many are in the exposure. No. You start with the exposure. Out of those people that are in each exposure category, how many have the hardcore? So you are trying, what you want to say is out of the people that know formal education, how many are employed? You want to compare with out of people that have primary education, how many are employed? Compare with people with secondary education, how many are employed? Compare with people with tertiary education, how many are employed? You want to see the employment increases along the trend, and that is what we have already shown in the first one we did. You will see if you scroll down and you see the statistics, it's the same. It will give you exactly the same. It doesn't affect the easy in your interpretation. The percentage you put, whether you say it should show euro or column, will affect your interpretation. It doesn't change anything in the statistics. The chi-square will be the same. The trend will be the same. Any question? That is how to do chi-square for trend. You remember the outcome variable must be two categories, and the exposure variable must be ordinal. It must be hierarchical. Any question? No question. Okay. If there's no question, you can stop sharing. Let's go to the next one. Let me share my slide. So that is it. And that's chi-square for trend. And this is just showing in my slide the step you take. So look at the results, the same result you have shown. So you see. So linear by linear is a chi-square for trend. Now let's look at the chi-square test of goodness of fit. Chi-square for test for goodness of fit is a single sample parametric test. This one now is a single sample. One sample is one group. Also referred to as one sample goodness of fit test. It looked like a one sample t-test, used to determine whether the distribution of a categorical variable, e.g., ABO blood group, follow a known or hypothesized distribution, e.g., a known pattern in the population. You know, in most literature, this ABO, especially in medical literature, this ABO group, blood group, is actually the example they usually give, because that's the one that really come to mind. Because you know, the ABO is a categorical variable. These 4 categories of blood of the blood group in ABO, either A or B or AB or O. So how do they distribute? If you gather all the population, if you do their blood group, what percentage is B? What percentage is O? What percentage is A? What percentage is AB? And it has been found that in many societies that B is the O, blood group O, consider the highest percentage, around 40 to 40-something%, close to half of the blood. So the majority, or we cannot say it's majority because it's not more than 50. There is not to 50%, but close to half of the population are blood group O. Blood group O is the commonest and is the universal donor. Anyway, and that is why God has made it also. Even because of that, it would have been terrible for mankind. But it's the universal donor, there is the commonest also, blood group. But they can only remove it, get from O. It helps them also because they are plenty, summer. If it is O also, not that they will likely see O because it's the commonest. They will likely see O to donate for them because it's only O that can donate for them. Now, if this if studies have been done in a particular population like that, and I say, oh, this is the proportion of this blood group, A, B, C. Now, in your own so I say A, B, C, A, B, and O. If there's a lab in that population, and as people are coming to the lab or coming to the hospital, and you take their blood, and if you do the blood group, you may see a pattern that may be slightly different. You may see, even though they say the O is 48, in your own it may be 42 or 40% of them. It may be even 50-something. So you may want to know for each category, maybe your own A is 10, B is 15, B is 25, something like that. Everything must add up to 100%. Now, you may now want to compare your own percentage from the theoretical. The theoretical one just mean that what has been done before for the population, which they believe that is the number. So I actually say, when I say something is theoretical, it does, in fact, the knowledge of the theory was gotten from practical. Because somebody practicalized it, and I say, this is always like this. When we begin to teach it over and over, it's always like it becomes theory. So when we say theoretical distribution, we are talking of something the practical has been done before that they believe. So we want to see this practical, this theoretical distribution, what is established to be known, is it the same thing as what I'm having now? That is, we are trying to do goodness of fit. Does it fit into existing pattern? What you have, does it fit into existing pattern? That is test of goodness of fit. The expected frequency for each group of the categorical variable can be equal or unequal. That is, in the expected frequency, that is, how it's supposed to be, can be equal or not equal. It depends. It's just like if you say that as we have 6 geopolitical zones now, we say that in federal character, it must be equal number. It may be consider that in any employment we are doing, should be equal number from each geopolitical zone. That's equal. But it may not be equal. We may say that, okay, the number for each from each geopolitical zone is proportional to the population of each zone. So it depends on what, and so because when you are running it also, that knowledge is there, must be there for you to understand, for you to carry it out. Now, how do you compute it? The example we have also is the example of ABO group. The table shows the distribution of ABO blood group in a tertiary hospital laboratory and the expected frequencies in the population. Can one infer that the distribution observed in the hospital significantly differ from that of the population. So if you look at the first table now, you see that A, B, O. So in your observed frequency mean in your own, in this 300 sample we are taking, 76 is A, 74 is B, AB 31, 119 is O. And if you put it in percentage, you see that this. The A is constitute 25.3%, the B constitute 24.7%, this AB constitute 10.3%, and O constitute 39.7%. But in the distribution of the population, the theoretical one is the one I put in this color. I don't know which color, is it orange now or whatever. So distribution in the population is A, what they are published before is 21%, 21.1. B is 18.9. AB is 50.4, and O is 44.6. All of them will add up to 100% also. Now, if you want to, you remember in our chi-square, the frequency observed minus expected square over expected. You've already gotten your the observed frequency at the 76, 74, 31, 119. Then you want to get the expected frequency. You know that the one they gave you before is the percentage, it's not the frequency. It's the relative, they call the percentage relative frequency, not the frequency itself. There's frequency, there's relative frequency. Frequency is the number of occurrence, while relative frequency is the number of occurrence expressed as percentage of the total occurrence. So it was the percentage you published, you know, you want to now convert it. If you apply that same percentage to your own present sample size, what you will get. So if you look at the second table, you see that A, you see the way the first column, the same thing as what we have before, second, third, then the percentage. When you now see the expected frequency, we are calculating it from the table above. And that's okay. The expected frequency you expect for group A will be, you know, it's 21%. 21.1 over 100 times 300. You know, the total is 300, your sample is 300. So 21.1 times 100, into over 100, that's 21%. Multiplied by 300, it gives you 63.3. It's not in percent now. That's the number, the frequency you expect. If this your observed and the expected frequency is the same, that's the frequency you expected. So you expect your own observed to be. So if, look at it now, you do it for the second one, 18.9 over 100 times 300, you do it for, so it will give you all the value like this. And if you add all of them together, it should be equal to the 300. So you have got, you know the observed frequency here, you know the expected frequency now. So if you apply the formula, you know there are 4 categories there. You are observed minus expected, square over expected. Look at it, 76 minus 63.3 square over 63.3. You do it for all of them. When you do it now, add it together. If the chi-square 40.464. The degree of freedom, because the number of category minus 1. So there are 4 categories of the blood group. So you now say 4 minus 1, make it 3. The degree of freedom is 3. The critical value for chi-square at the degree of freedom of 3, if you look at that table, is 9.488. And the 14.464 is bigger, far bigger than that. That should have is significant. So the distribution, your own observed value, is significantly different. It's not the same thing as what operates in the population. That was, of course, you cannot calculate with hand, you cannot calculate the p-value. You can only go to the table and say, oh, the p-value will be less than 0.05. Thank God for computer that is here to say. So let somebody, this is the step you use to do it. Let somebody now share ABO blood group. There's a file also sent to you. One of the 5 ABO blood group. Let's look at it. Is somebody there to do it? Is somebody there?
Yes, sir.
Okay. So let somebody share. Share the ABO blog group. Or let's ask for, is there any question? When you do ask question like that, I don't know, maybe you just, is it that it's very simple to grasp? It's well explained, or it's quite confusing? Some people say, hey, don't worry, I will get to know it later. I will know it later. No, know it now. Dr. Lamingo, is it that your old computer that you are using?
Yes, I'm sharing.
Okay, it's taking time. I say, is that your old computer?
Yes, sir.
You're laughing. You know what we call them, the old computer, they are locomotive engine.
Yes, sir.
You need to replace them.
Yes, sir.
Well done. Okay. Yes, you have shared. Yeah, that's great. Now, if you look at it, all we need to know, the A, B, you see we have already coded. If you look at the A, if you want to know, one is A. If you want to know, go to, it's not showing some icon for us. I want to go to view.
Okay.
It's doing what is happening to Dr. Jamil the other time. I want to go to view. If you click on view now, you check value label. If you check that value label, yes, look at the view. Yes, it can show now. Click on the view. Look at, come down. You see that value label after the grid line. Value label. Just check that box. Check. Click on it. Can you see now? That label is A. A that is good 1. B is 2. 3 is you know, we enter it. You enter it as numeric. It will label it. But if you don't want to see it, you can go back. If you don't want to see like that, you just want to see the something, you can go back to the something and uncheck it. Now, it doesn't really affect your result. It doesn't have anything to do. Now, analyze. So if you look at it, it's only the block group. It's not, you don't even, the age, the sense, whatever is that data is not useful to you for it because it's only that block group you are targeting. So it's not frequency. That is the exception when we say constability. But this one, go to non-parametric. You know, chi-square is a non-parametric statistics. Slow down. No, don't go to descriptive, go to non-parametric. Go to legacy dialogue. Go to chi-square, you see chi-square there. Yeah, click it. Yes. So variable you are interested in is block group. Yeah, move the block group in. You will see under all categories equal. Just click OK. And click value, rather, click value. Because not all categories are equal. If let's say it's all categories, I just click OK now. You just run it. Will assume that the expected frequency is 25, 25. You know, there are 4 categories. If 4 categories are equal, the expected frequency will be 25, 25, 25, 25%. So the team, the computer just assume that and just go and run it for you. You don't even need to stress yourself, just say click OK. All categories are, you just put and say click OK. It will assume that it is only applicable if the expected frequency is the same. So when you're having 4 categories, it will be 25%. If there are 5 categories, it will be 20, 20, 20%. Now here, the all categories are not equal. As we have done it, it's not equal. So you click value now. Click value. Under the value now, type the first category. What is the expected frequency for the first category? What was the expected frequency? Somebody should help us look at it. Okay. Okay, maybe I should have, wait, let me share first. I'll stop sharing. I will override it. Let me share so that people will receive the value on my, on what I did, yes, on my presentation. I will override the share now. I will share my. Yes, I'm coming back now. Just wait. So the expected frequency, 63.3. Okay, let's go to that table you saw. 63.3. Somebody should write it down. 63.3. You must know that when you are putting it. Yeah, 56.7, 42.2, 46.2, and 133.8. So let me stop sharing. So you can share again, Dr. Lamingo. Share again and continue your work. I will provide the information to you when you get it. Okay. Now, click under that value now. Click 63.3. That's the first category. You know, that is why it's good. You know, you have already, that's why it's good to use numeric so that you number one, you have already coded A to the 1. So that's why I will follow it. You attach this 63.3 to A. Add, click add. The second one, go back there and type 56.7. Yeah, 56.7. Add. And type 46.2. Add. Then the last one, that 133.8. Add. Click OK. So stop sharing and share the result because the result is not showing us now. Stop sharing and now share the result. The output. Stop sharing. You have to. You cannot share the. It will not allow you. The Zoom will not allow you. You won't be able to see. Stop sharing it first before you can. You cannot go and overwrite it. It will not allow you to overwrite. You won't see it. Stop. There's an icon red. Stop sharing. Click on it. It will stop sharing. Now share again. You'll be able to go and clear hands. Now go share screen now. You'll be able to see the result output and you click on it. Yes, great. You see that, can you see? You see A, it gives you the observed frequency, 76, expected frequency, just one. Sorry. You see 76, 63.3. You know, the expected is 63.3. Then for group B, 74 observed, expected 56.7. So the other one, 31, there's very 46.2. The other one, 119, there's very 136.8. So the residual is the different in each of them. That's why they just give you the difference. You will notice something that the one that has some are positive, some are negative. But if you add the two positive together, it will give you exact the value of the negative value. So if you add 12.7 plus 70.3, it will give you the same thing as 50.2 plus 40.8. But that's the nature of chi-square. And that is why you have to square it. Otherwise, it will amount to 0. But if by the time they square it, if you look at the calculation with it, those are the differences you see. The difference between observed and expected. Those are the things we square. When you square them, you now divide by the expected. It give you add it together, it give you something. Look at the degree of freedom is 3, and the p-value is 0.02. So any question, so you can do the chi-square for we have done 2 things now. Chi-square for trend and chi-square test for goodness of fit. Any question? Is there any question? No question.
Sir, my question.
Go on.
So are we still going to do manually to get the goodness of it that what you just did? That's expected
we have
to
done
get
it manually. We have demonstrated it manually now.
I know. I'm just saying normally. That's like routinely you must
No,
do
you
normally.
don't do it manually. No, you don't do manually. Once you enter your data, you run it, and this is chi-square now. You run it.
Okay.
Yes, I'm now. You know the expected you put there. Yes, the one you enter. You know it's the theoretical one they have given you from literature. That's your that's 63.3, 56.7. All those one. You calculated it from the percentage they gave you.
Okay.
And you apply the percentage to your own sample size to know. Yes, I mean now. So the only way, the one that you don't need to even put anything, if all the categories they are equal, if let's say they are equal for the 4, you know the computer has already given you the option. Just say, okay, that one is you divide it into 4 equal parts for them automatically and run the result. But if it's not the same, so you have to calculate, yes, you have to calculate what the frequency means. You have to apply the percentage to your own sample size. Yes, I'm now. You apply the percentage to your own sample size and run it. Does it make sense? Okay, you can stop sharing. Let's move forward. I share my own slide. So if you look at it,
hello, sir.
Yeah, go on, Ben.
Okay, at the point my audio went off.
Okay.
So I want to find out, is it from the data we are getting this expected figure?
It's not from the data per se, but from the samples, your sample size, and what you have got in literature as the expected percentage. You know, they will have published, maybe like this blog group, and they have published that in this population, in a particular population, A is 21%, B is 90%, AB is 50%, and O is 45%. Yes, I mean, they have published it, and that's what you are using in your own data. The only thing you want to use together with it in your data is your own sample size. So when you now apply, okay, what is percentage? What is 20% of your sample size? What is 90% of your sample size? You know, so you want to apply that percentage to your own sample size. That this data I have, if I have to apply that percentage, how many of it will be 21%? How many of you will be 90%? How many of you will be 50%? You get it now. For you to get the expected frequency. So when you are now running it, you now feed those expected frequencies into that computer. That's all.
Okay, thank you.
You're welcome. So now, We have done that. Let's forge ahead. This one just a slide to show. If you look at the result, the same result you get. Let's talk about Mach-Nehmer chi-square. Mach-Nehmer. So, what Mach-Nehmer does is quite interesting. Quite interesting statistics. It compares proportion between two related groups, repeated measure of peer observation, with variable having two categories of outcome, yes or no. Example is just yes or no. It can be anything but two categories. So whenever you have a categorical variable, it's only two categories, either yes or no, he, no, he, diabetic, not diabetic, hypertensive, not hypertensive, whatever. And you assess it, you assess that particular outcome on a group of people on two occasions. Let's remember, it's categorical outcome. You assess it on two occasions on the same group of people. It's not two groups of people on the same. The example we have now, look at it. The table below shows the hypertensive status of a group of adults before and after an intervention that involved lifestyle modifications. Did the intervention significantly influence their hypertensive status? Look at the table. You see, on the horizontal axis is hypertensive before your intervention. Hypertension. You want to see how many were hypertensive, how many were not hypertensive. If you look at the total for years, that 60 out of 200 people, 60 of them were hypertensive and 140 were not hypertensive. Maybe after you take their blood pressure, you say, oh, say if it's above this, say, oh, this one is hypertensive, this one is not. You find out that out of the 200, 60 were hypertensive. Now, after you have taught them how to exercise, how to eat this, lifestyle, many things they should do, after some months or maybe years, you now come back to the same 200 people. It's not another set of it. It's not another group A or group B. No, it's the same group, one group. You now come to do the same thing, to assess, measure their blood pressure, and classify them. Of course, from that, you know that there will be some people that were hypertensive then. When you classify again, they're still hypertensive. Some were hypertensive then. They are no more hypertensive when you classify again. Some were not hypertensive then. That became hypertensive. Some were not hypertensive then. They are not still hypertensive. So those are the four categories you're going to have. And those are the four categories, because after you have done it again, you now discover, look at hypertensive after. Under years, the total is 40. Now discover that 40 people were hypertensive. Then 160 people were not hypertensive. You know when you started, 60 were hypertensive, 140 were not hypertensive. When you now finish now, you have reduced the number of hypertension to 40 and with 160 not hypertensive. So you want to see this reduction. Is it significant? This reduction, is it, maybe my intervention, what I did, I really helpful. I've slowed down the number of those people that were hypertensive. You have 20 people that are no more hypertensive. You want to see, is it significant? That's what Mach-Nehmer does. He tries to compare a dichotomy outcome, categorical outcome, like binomial, like binary. Want to compare it before and after on two occasions. Measure it on the same setup. So it looks funny. So if you, of course, if you do a 2 by 2, is it going to give you 2 by 2 contingency table like this? If you do look at the first table I have here, try to explain it. Outcome 1 here, which is yes, hypertensive. Outcome 2, which is no, not hypertensive. Then here is the same thing. This one is before. The vertical one is after. Outcome 1, outcome 2. Yes, no, hypertensive. Sorry. Now, you will notice something. You will notice, if you come to the example we use, you see that. What can you say about which there are, these forces, they call 2 of them concordant cell. Two of them discordant. So this is a workshop. Let's learn our voice. Which of the two cells are concordant? Which of the two cells are discordant cells? Let's think. Let's think.
So the concordant cells are those one in A.
A.
Yes, I can't see the second one. A and let me see.
You are not seeing my screen?
Now, okay, let me see. I'm coming. I can't see the second one. More better.
But my screen is clear now.
Maybe it's from my own end. Yeah, it's making.
Okay.
Let me see. Okay, let me see. Okay. Oh, sorry. Sorry, 1 minute. Okay. I know that. Yes. The concordants are cell A and cell D.
Okay.
Concordance.
Yeah. You are right. Because you see where yes merge yes. So for in our example now, okay, even in the diagram, the first table you see A is outcome 1 cross outcome 1. Both of them meet. That's concordance. If you see D, outcome 2 cross outcome 2. But if you see B, you see outcome 1 cross outcome 2. C, outcome 2 cross outcome 1. So those are the discordant. If you come to the example we did here, 8 people were hypertensive before, they remain hypertensive even after the intervention. 108, which is D, were not hypertensive before, they remain non-hypertensive after the. Those are concordant. They were the same state, they didn't change. So whatever you do has nothing, it doesn't move them. Now the one that changed are the discordant. This B, 52 now, you see that 52 were hypertensive before and they become not hypertensive after. Before they were hypertensive, later they become not hypertensive. And 32, they were not hypertensive before, but they become hypertensive later. So both 52 and 32 are discordant cells, that is cell B and cell C. So it's not only applicable to this, even when you do 2 by 2 table, you know. If even when we do diagnostic test, disease, non-disease, test positive, non-positive. So please, Dr. Jalil, you can mute yourself after you have answered.
Okay.
Because you are having a nice time at home. So can you see now? So it's good for you to know because there's implication. It has implication. Now I will come back to explain the degree of freedom. Let's solve this thing first because I don't want something that will be it's a bit complex for you to understand. But let's solve it to come back to the degree of freedom. Now, if you look at it now, we have already said, okay, 52 and 32 are the discordant. So, well, we want to know if this intervention has done anything. So, you don't have business with something that doesn't move. 8 were hypertensive, 8 of them were hypertensive before and after. 108 were not hypertensive before and after. It doesn't concern you. Leave them out. Okay. What concerns you is these people that change. You see some number of people change from hypertensive to non-hypertensive. Some people change from non-hypertensive to hypertensive. But we still want to see averagely which direction. Can we say this change is significant? Now, I want to ask a question also, because it's a workshop. Because McNema is very better. You need to reason logically to conceptualize it. Now, if no hypothesis were to be true, this change the number that changed from hypertensive to non-hypertensive should be equal by the number that changed from hypertensive to non-hypertensive. If non-hypertensive were to be true, the change in those both directions should be the same. Eventually, it's like motion without movement, oscillation. You move, just like you carry something, somebody return it. You carry it, you return it. Yes, there's motion, but there's no movement. So that is what's supposed to be. If not, I put it through that. Look, there's no difference. This your intervention did not do anything. Whatever the movement in one direction should be equal to the movement in the other direction. Now, if no hypothesis was to be true, you know that it will be expected value. What that if no hypothesis to be true? What is the value? What should be the value inside that instead of 52, and what should be the value instead of 32? Who can give me? Because you just need to listen. Who can tell me? What should be the expected value now? The expected value to replace the the observed value for this one is 52. Say P. The observed value for say C is 32. Those are the two cells we are concerned about. Then what is the if no hypothesis was to be, what should be the expected value?
The average of the two.
Yes, the average of the two. Yes, that is, if you now add the two together, 32 plus 52 should give you 84, whatever, and you now divide 84 by 2, it gives you 42. You get the picture now. So if you look at the table here, the way you calculate the expected value now. For each of them, 52 plus 32 over 2 is 42. 52 plus 32 over 2 is 42. So it should be equal for both of them, right? Now, the intelligence, if you do it like that, you can just put it, apply the formula. Is of that minus expected square over expected. Just do it like that, it gives you your answer. It gives you the value. The value you have with 4.76. And usually degree of freedom 1. You know that for the degree of freedom 1, the critical value for chi-square is 3.84. And this one is 4.76. You know that automatically the p-value will be less than 0.04. Then the alternative way of doing it is this. Did I put it on the of calculating it? Is this. Instead of you using that formula, look at it. You can just say these two values, the difference between them, you square it over the addition of the two. So 52 minus 32, 20. You square 20, it's 400. Over 52 plus 32, 84. To give you 484, it gives you the same value. Can you see? It's a fast way of doing it. Rather than saying observed minus expected. So it's intelligent people that discover it too. And to calculate the degree of freedom. No, I was telling you the other time. The degree of freedom is the K number of category times number of category minus 1 over 2. How many category of the article is 2? So K 2 times 2 minus 1 over 2, making 1. This degree of freedom score, calculating it, you'll be surprised. You see, when we get to Magnum Barker, that's where it will interest you better. So let's go and solve this thing. We have to run it. It's very simple, just ordinary cross tabulation. The one truth will come to you, by that will run it. So who will share with us? Somebody should share with. These are the steps in running. They don't want, I will just explain it. Tell you. Who will share the screen with us is hypertensive before and after. There's a file, data file among the file I sent to you, hypertensive before and after. The hypertension before and after. Okay, somebody has shared. Yes, Dr. Lamingo was chair. Yes. So this is it. Let's see the data view. Yes, that's great. Now, if you want to go and view it now, you can see that it's labeled, it's well labeled. You can go to view to check. Yeah, labeling. Or, can you see? Or if you go to your variable view, you see how we label it. In variable view, that's where we do the label. We say one is equal to 2. And this one, we have done that when we say using on our in our workshop on using SPSS last week. That was why it's good. By the time you are coming for this workshop, it's good to have had some background knowledge. So, okay. Analyze now, Dr. Lamingo. Analyze. Cross descriptive statistics. Go to cross tab. Click on it. So which one should be on the row? Which one should be on the hard copy now? On the column. I want to be asking you because it's a workshop that we are working together. Somebody is
before should be on the row.
Yes, before should be on.
Before.
Just one. Yes, that's great. Go to statistics. You see McNema. Can you see down on the left side? McNema. Yes. Continue. You don't need to bother yourself about the cell because you don't need that percentage per cell. It's not applicable here. It doesn't make sense here. Click OK. So the result is there. You may need to stop sharing and now share again. And now share your result output. Now share your result output. Yeah. So that you will see that you see under chi-square test down. You see that table, you see the table show you yes, no, all those ones. It's the same thing we have in our example. No, you see the concordance, discordance, all those ones, you see them there. You see that the total is still 200. Under the before, hypertensive before, under years, the total is 60, hypertensive before, and no under no 140 were not hypertensive. For after under years is 40 hypertensive, under no 160 were not hypertensive. Now, if you look under the McNema, there's nothing there apart from Valley KC 200, but under the exact test, it gives you 0. Either the p-value, it gives you 0.038. You know how the way that McNema is simple to calculate. No software are able to bring the result out. I don't know why. God is great. It's only human brain that can calculate it. They have not been able to bring, I've not seen software that calculate that McNema and bring the result out. Either if you see anyone, let me know. I've not seen. And but you give you the p-value, but you can calculate with your hand, you can calculate the McNema, especially through that short method. And you cannot calculate the p-value. You cannot calculate the p-value, but the computer will calculate the p-value for you. So in McNema, it's here is the joint project. So you calculate the McNema and enter the result. The computer helps you generate the p-value. Any question? Any question? And the degree of freedom is surely 1. Any question? Please ask question. Is it that it's simple, right?
I think it's okay, sir.
That's great. That is great. Now, so you can stop sharing. Let's proceed. So we have learned chi-square for trend, chi-square for test of goodness of fit, chi-square, McNema chi-square. So we still have some to learn. Now we want to quickly go to McNema-Bowker. McNema-Bowker test. So this is the result we just did in our displays now. So McNema-Bowker chi-square. This one is an extension of McNema. You know, McNema O, you are dealing with the outcome variable is 2 categories, either yes or no, or there, not there. But whenever the category is more than 2, you are having 3, 4. So it's a little bit complex. And of course, it's the same logic of McNema. So Bowker also now join put mount to extend it. That's why they call it McNema-Bowker, because it's the logic behind McNema test, but it's now applying it to bigger contingency table. I will just let me just read through this preamble. I will not bother you with this table. You see, it can be confusing, but I have the one I put data in. I prefer using that one to explain. But this is just for theoretical. You know, some people like theoretical thing. What is the basis for this? They want to know, and that's why I put this one here. But for me, anything n does not make anything. It's what you make it look like that it is. So given n subject from whom measurement were taken twice, you know it's before and after. You already said it. With the outcome of each measurement assigned one of k categories. When I say k categories, let's say, let me be fluctuating between this slide and this next slide. Oh, not this one. For example, now, the example I have here is socioeconomic class before and after COVID-19 pandemic. You know, this COVID-19 may make some people poor, may make some people rich. Some people are better off. You remember when they said there was lockdown, they say it's only food seller that can go out. You know, the food seller that can supply essential goods. So the food seller, they were making money, so much money during COVID-19. Where any other worker failed, they were going out. So it's possible some people become poor, or they are become their socioeconomic class fall after COVID-19. For some people, it will go up. So we are looking at socioeconomic class in the context of upper, middle, lower. So what is the socioeconomic class before, then after? So the socioeconomic class has 3 categories. That is the K category. So that's what I'm trying to explain in that place. So when you say that measurement outcome of each measurement assign one of the K categories, that is the K category, 3 categories. One of them, you can only belong to one or the other. You are upper, middle, or class. For the example we just gave. This situation can be represented as K by K contingency table. That's what you see. 3 by 3 contingency table. If it is 4 categories, 4 by 4 contingency table. It also be like that. It cannot be K 2 by 3. It cannot be 3 by 4. No. It is 3 by 3, 4 by 4, 5 by 5. Because it's the same category you use before and after. It's the same variable. So that's why we call it K by K contingency table with entries, these are different type of cells. So leave all those jargon. Let's just go straight to explanation. Now, what all this one I put here, I don't want to. I will come back to it to explain, because I always look for the simplest way for you to understand it. Not necessarily the way it was arranged, but the simplest way for you to understand it. For this example now, the table will show the socioeconomic class of a group of adults before and after COVID-19. Did the pandemic significantly influence their socioeconomic class? Now, how do you compute it? You see, observe table now. You see that when you look at it, okay, before the total is 300. You know, it's the same data we are using. We have used socioeconomic data. The total is 300. You can see at the base here. Is it? Total is 300. The number in upper class before COVID-19 out of 300 is 35. The middle class 100, the lower class 165. After the COVID-19, the middle class is 35. In the upper class 35, the middle class 100, and this one 165. But it doesn't mean there is no movement. It just happened like that. Just happened like that. Now, there are some things, you know, when we were dealing with McNamara, I asked you concordance and discordance. In this case also, we have concordance cell and discordance cell. So maybe though it's a little bit complex, I want to see if somebody can explain again. Which one, just give me an example of maybe concordance. What are the concordance cells here? Forget about even the which cells are concordance cell here?
The one, upper, middle, lower. That is the white ones.
Yeah.
Concordance.
Yes, that's great. That's a very good answer. So, any objection? Is anybody, is it confusing anybody? That white one, they are the concordance cell. If you look at it, that is upper. The person was in upper before, is upper after. The middle, you were 36 people, they were middle before, they were middle after. 93 people, they were middle before, they are middle after. Is it clear to everyone? Now, those are concord. If you look at it, because it's not 2 by 2 table now. No, in 2 by 2 table, because there are 4 cells, 2 are concordant, 2 are discordant. But it's not like that here. Because it's more than 1 category, 2 categories, can be 3, can be 4. This example now is 3 categories. So this discordant cell may not be equal to the number of concordant cells. The diagonal, just like along the diagonal is the concordant. Off the diagonal is discordant. This discordant, they occur in pair. They occur in pair. If you look at it, look at the one is it purple that look like purple color? This one, this one, they are the discordant. You know what? This one was upper before and middle after. This one was middle before and become upper after. Can you see now? They are the corresponding discordant cell. Upper before, this 14, upper before, middle after. This 7, middle before, upper after. Look at the green one, they are the corresponding discordant. This 15 was upper before, lower after. The 22 was lower before and upper after. Can you see? These blue ones, they are the corresponding discordant, another corresponding discordant. 57 was middle before and lower after. 50 was lower before and middle after. Can you see? So the logic here now is that you will see a trend from this table. You see, the number of discordant will be equal to the number of categories. You have 3 categories of the outcome: upper, middle, lower. And that's why the number of discordant cells, they are 3. Now there's another thing now. Then the number, the pair, the discordant cell occur in pair. And it's the same thing, 3 pairs of discordant cell. So it's telling you that the number of discordant cell will double the number of concordant cell. They will occur in pairs. And that shows that if the category are 3, the number of discordant cell, concordant cell will be 3. The number of discordant cell will double, it will be 6, but they will be in pair of 3 pairs. Does it make sense? So if you come, now, this one is just to throw some academic something into it, so that number of categories, 2, 3, 4. If you remember the number of categories is 2, that is the one for McNema itself. The anything from 3, 4 and go is McNema Bowker. So when the number of categories is 2, remember the number of cells will be 4. When the number of categories will be 3, 3 times 3 will be 9. Number of categories is 4, the number of cells will be 16. It's square of it now. You know, you can say 5 by 5. You know that it's going to give 25 cells. So the number of cells will be K times K. The number of categories is K. The number of cells will be K times K. Then the number of discordant cells will be K. I've already told you. You can see on the graph, on the table, that the number of this concordant cells will be equal to the K number of categories. Then the number of discordant cells will be 2 times the K. No, not necessarily 2 times the K per se. Not necessarily 2 times the K. Is going to be, that is where the calculation is going per se. Then the pair of discordant cells, can you see the pair of discordant cells? Now, if you remember, whenever you say you want to, how many times where you can compare, you can arrange things. Like if, for example, now you want to do, you can pair things. If you have 3 groups, how many ways can you pair 3 groups? And pair them in 3 ways. You have 3 groups, A, B, C. You can pair them either A and B, A and C, and B and C. That's why. That is the number of the discordant pair. Can you see? If you remember, for McNema, the number of discordant cells and concordant is just 1. Can you see? The pair of discordant is just 1. But when you are having 3, the example we are showing now, the number will be category will be 3. If there are 4 categories, it will be 6. If you have 4 A, B, C, how many ways can you pair them? Is 6 ways. A, B, C, A and B, A and C, A and D, B and C, B and D, C and C and D. Can you see 6 of them? If you have 5 categories, how many ways can you pair them? Is 10. If you have category A, B, C, E, it's going to be A and B, A and C, A and D, A and E, that's number 4. Then B and C, B and D, B and E, C and D, C and E, and D and E. It's 10. It's like that. So what this was just showing, this was applicable when you are say how many, if you have 3 groups, how many t-tests will you go and do? You have to, when you want to calculate, when you get to ANOVA, you're going to see family-wise error the same way. So that's what that table is just for that. So let's just leave it. You don't need to cram that one. It's just for you, if you can understand the concept here, be able to know. So now, you know that the chi-square, as I said, as you see that there are 2 ways we calculated McNema the other time. You either use the formula observed minus expected square over observed, or over expected, or you just see the discordant, the difference between the discordant and concordant over the addition of discordant and concordant. Whichever way you do, you get the same answer. Now, let's just do what is very paramount now is how do you now calculate the expected value here? You remember that in that business, now the concordant has no business with them. So those discordant, they are the ones that are useful because the discordant they didn't change. The concordant they didn't change. The discordant that are useful in the calculation. For example, now, just like the way we calculated it for McNema, the way this one occur in pair, you calculate it from the pair. For example, this 7 and 14 now, all you need to do 13 plus 7 over 2 will give you 10.5 for both of them. If you look at the green one, 22 plus 15 over 2, it gives you 80.5 for both of them. The blue one, 50 from 57 divided by 2, it gives it 53.5 for both of them. That's how to calculate the expected value. And you can go and feed in observed and unexpected, all of them. So, you know, all those discordants say, how many of them? There are 6 here now. All the diagonal, now compute it for them. Calculate your McNema Bowker. Can you see? So now the degree of freedom here is, we have already said is k minus 1 over 2. K means 3 here. 3 times 3 minus 1. 3 minus 1 is 2. 2 times 3, 6 divided by 2 give you 3. The degree of freedom is 3. So of course, you know that this chi-square is not significant because the critical value for the chi-square at the degree of freedom 3 at the 0.05 level of significance is 9.488. So the calculated chi-square is far, far below. So there's no association. So chi-square of this is not statistically significant. This other method where you say, this other one here is, how do you do it? The way you say, the difference between the concordant square over the addition of the concordant. When you do it for the 3 pairs, it gives you the same, whichever way. Any question? We want to go around it. It's very simple. It's the same way you run the this thing. So we are using the socioeconomic class. This is our data we used yesterday. The data is there for the social. You're going to see that we have socioeconomic class after and before and after. So somebody should read it. It's not difficult. It's the same way we run. It's the same way, just run the McNema. All this one just for you to be able to conceptualize this. So who is sharing? Who is sharing? Share socioeconomic data. The one we used yesterday. And we also use it today. That's what we use for the trend. Chi-square for trend also. Who shares? Yeah, that's great. So let's scroll to, you see, if you scroll, you see, where is it? There's, this is removing. You see, so SEC before COVID, SEC after COVID. Can you see? Socioeconomic class. So go to analyze. Descriptive, cross-tab. No, it's cross-tab now. Click, that's not the thing. You click, it's on, it's cross-tab. Cancel it. When you get to descriptive, descriptive statistics, you now go to cross-tab. You are not going to descriptive. No, you don't know how to, you have to first of all move along here. Cross-tab, yes. Now, COVID before will be the row, SEC before COVID, SEC after COVID. Go to statistics. click McNema. But when it does it, it will give you McNema Barker. Click, continue. Okay. So stop sharing and share the result with us. Yes, scroll down. You see that this one is different. Can you see? You see the table now, it gives you concept just like the way I arrange it on the table like that. You see the along the diagonal 636, 32 are the concorder, while the other one are the discorder. But look at it, this one was able to give us McNema Barker. It's only the McNema when you are talking about 2 by 2 that they can't compute. But it was able to compute McNema Barker, give you the degree of freedom is 3, and this is the p-value. Very simple. Any question? And whenever you are dealing with this McNema Barker sort, those percentage, they are useless because the way we arrange the table is different. You only put along the periphery, you put, if I want to put this one in the result now, is this total horizontal is for the after, total vertical, here, I shall see, is for the before. Anyway, you can call it, though this is where it looks vertical, but this one here is total horizontal, socioeconomic before, and total vertical is socioeconomic after. If I want to put percentage, what I do is that 35 over 300, I put it from 100 over 300. This one, we do the same thing for this one. That we don't put the percentage in the one in the middle because those are the changes. But when you arrange this table like this, you put the percentage along the periphery like this. Any question? Is it confusing? No answer.
It's not confusing.
Okay. It is very straightforward, right? Okay. That's fine. You can stop sharing, Dr. Daniel. You see that they are very straightforward. Now, these are the steps you just went to, and this is the result you generated. That's what you got. And so if there's no question, any question concerning, I say I wanted to explain something, what we did yesterday, but I cannot remember what I wanted to explain. These people, can you imagine, even Dr. Lamingo, not Lamingo, where is Dr. Lamingo? Is out. Even the 2 people that they said they cannot make 5, but even the 6, they are 6 o'clock, they are not here. This is to 7. Even Dr. Lamingo, maybe it's the network that knocked him out. Okay, let's proceed. Cannot wait. So now, any question on the chi-square we have just discussed, all the chi-square, because we want to move to measure of association now. So I want to give a background against what we are doing fully tomorrow, which is relative risk and odds ratio. There are some concepts you need to understand to be able to grasp relative risk and odds ratio. We can discuss that. If there's no question on what we have done so far, any question on what we have done so far? Because I want to bring the slide, this other one now. So it's so simple. Okay, if it's so simple like that, let's continue. So let's quickly look at measures of association. Under this, we'll be looking at understanding the following concept: risk. What does risk mean? Because you'll be hearing relative risk. What is the meaning of risk? You will be hearing odds ratio. What is the meaning of odds? Before you know the ratio. You know, odds ratio is the same thing as relative odds. Relative risk is the same thing as risk ratio. Whichever we want to first of all understand the meaning of risk. We want to, well, now we go to understand relative risk and odds ratio. We run with spaces, interpret odds ratio, relative risk at their 95% confidence interval. And you good to know that it's good to know that if you want to publish in high impact journals, medical journal like Lancet, nobody take p-value from you. Don't take p-value from your those hypothesis tests. They prefer confidence interval. Either you say difference between means and the confidence interval, or odds ratio, relative risk with the confidence interval, or hazard ratio and the confidence interval. So let's quickly look at what is risk. Another name for risk is actually probability. You know, probability is futuristic. Say, what is the probability that this one happens? If something that has happened, nobody will ask you what is the probability that it will happen. Or what is the probability that it has happened? It has happened now. It's something that has not happened that you calculate this of it happening. Probability, risk is the probability that a particular event or outcome will happen over time. But over the many people think risk is all about something will not happen according to plan. Hold on. Okay. So maybe something, they think maybe something will not happen according to plan. They think that is risk. But that risk is probably that event occur. Because English usage of risk will mean that something bad happens. But there is also what they call speculative risk also, that it may be both ways, that is good or bad. People that get involved in investment, they take risk, they say they take risk. They know that they can win jackpot, they can make it, they can lose money also. So they can make profit, they can lose. So it both with that what we call speculative risk. Risk is actually probability. Now, if you understand probability is the number favorable to event over the total number, and yes, over the total number of possible outcome. The number of outcome favorable to the event, like for example now, if you have what do I call it? Okay, you toast a die. That has 6 faces. You say what's the probability that you get 2? You know that out of the 6 faces of the die, only one they wrote 2. So the risk or the probability of you getting 2 is 1 out of 6 over 6. So once you know that risk is the same thing as probability, I don't think you understand. You find it difficult to understand risk. The odds is the one you may find difficult to understand. Odd is risk over 1 minus risk. That is the probability of an event happening over the probability of an event not happening. You know the probability of an event happening is the risk, while the probability of it not happening is 1 minus the risk. Because if you say probability that it will rain today is 0.6, of course, that's 60%. The probability that it will not rain is 0.4 because it's 40%. You remove 60 from 100%, it give you 40. Now, odd is risk over 1 minus risk. So if I say probability that it will rain today is 0.6, 60%. 0.6. What is the odd that it's rain? Please, it's a workshop. Let somebody calculate it. I don't know if you are following me. If the probability that it will rain, let's say tomorrow, is 0.6, what is the odds that it will rain tomorrow? Nobody? Dr. Ganiyo, are you there? Dr. Ben?
Yeah, but I didn't get it well, so.
I said that what I show now, what I am sharing, I say risk, odd is risk over 1 minus risk. And risk is probability. Yeah, let's say, it's like say, odd is probability over 1 minus probability. And I say, if the probability that it will rain tomorrow is 0.6, what is the odds that it will rain tomorrow?
Based on what you said now, 0.6 over 1 minus 0.6. So to be 0.6 over 0.4, which is let me say 3 over 2. That's 1.1 or something.
Yes, 1.5. You're right.
Yeah.
So because when you finish, thank you. Just off your this here. Thank you, because you are enjoying yourself at home. Now, you will notice something from what he said now. You know that probability can be from 0 to 1 maximum. It can be 0, it can be 1. They cannot be less than 0, cannot be greater than 1. But the risk, the odds, probability is risk. So risk can only be from 0 to 1. Cannot be greater than 1, cannot be less than 0. But all you can see from what you are calculating, all can be greater than 1. But it cannot be less than 0 also. From 0, you're going to know later that it's from 0 to infinity. Now, if you change subject of formula now, risk will be odds over 1 plus odd. No, odd is risk over 1 minus risk. Risk is odd over 1 plus odd. Now, look at the table beside. You will see, if you calculate, look at the probability. Different probability from 0 to 1. Can you see? Different value of probability. This corresponding odds. This probability is the same as risk. Different value of risk. If they calculate the same odd for that probability, you will see that where probability is 0.5, that is halfway, because it's usually between 0 to 1. Halfway is 0.5. When probability, which is the risk, is 0.5, the odd is 1. How do you know? Okay, depending on answer me the other time, I want you to calculate it. If the probability, the risk or probability that it will rain tomorrow is 0.5, what is the odd? Please calculate it. Say it the way you say it the other time. If the probability is 0.5, what is the odd? If the probability that it will rain tomorrow is 0.5, what is the odd?
It's 1.
1, thank you. Because it's going to be 0.5 over 1 minus 0.5. That is 0.5 over 0.5, which is 1. So when the probability is halfway, it has traveled its own half journey to the highest point, 50%, the odd is 1. Now, if you now begin to move from that place for probability of 0.9, or the probability above 0.5 to 1, as you are moving closer, the odd is going to infinity. So, okay, now I want you to calculate it again. If the probability that it will rain tomorrow is 1, what is the odd that it will rain tomorrow? Say it out to his workshop.
It's infinity, sir. 1 over 0 is infinity.
Yes, because it's going to be 1 over 1 minus 1. And 1 minus 1 is 0. 1 over 0 is infinity. So when risk is approaching 1, starting, the odd is approaching infinity. Let me tell you something. The people, if you look at it, because the value of risk, which is probability, is confined between 0 and 1. So sometimes it is easier to use odd because odd can have extremely large value. You'll be able to know the difference. There's a big difference between this odd. Sometimes when the risks are very, you will not be able to decipher that this risk of this are they close. The people that speculate, that bet for football, that speculate about who will win, who will not win, they use odds rather than risk because we will calculate, when they calculate the odds or the probability of the risk or probability of maybe two teams or 2 clubs winning, if they convert it to odds, the odd will be able to give them, if there's more gap between the two. So the one that have a slightly larger gap, they know that this one is more likely to win. So they use odd, or they don't use risk because the risk will not allow them to really differentiate which one, which one the gap between them. But the odd will allow them because the odd give a similar, it's from 0 to infinity. And as you progress to look at odd ratio and relative risk, you're going to see that the value of relative risk also is narrow, while the value of odd ratio is from 0 to infinity also. So if we look at what I put down, odd is called the probability of the event over 1 minus probability of the event. That's what we just said, P over 1 minus P, or this. Now, if you look at it pictorially, or look at the picture now, probability, if you have a sector now, that's this red area of that circle of the circle, the probability is that sector over the total. If you say, what is percentage of, what do I call it? Maybe one ethnic group now in Negro, what is the percentage of the Shekiri? If it is out of 100, if there are 2, so it's 2 over 100, not 2 over 98. You will not remove proportion. Probability is proportion. Is part of the O. 2 out of 100. That 100, the 2 is also still part of the 100 total. 2 over total. Then for odd, 2 over 98. You have to remove that. You look at the sector, they have chopped out that sector out. 2 over 9. That is the probability over 1 minus probability. No, the probability now is the sector. The 1 minus probability is what remains, the sector that remains. That is what, can you see it pictorially? So in a rare disease, if the disease is rare, the odds, that if that sector is very small, the odd is equal to probability, close to probability. If, just like you see, if you look at the table we have here, probability is 0, the odd is 0 also. When probability is 0.001, the odd is 0.00001. It's very close. When that attribute, the probability is very small, the value of odd is close to that of probability. But as the probability is becoming bigger, the value of odd is becoming bigger. It is becoming bigger than that of risk, lack of probability. Until when it is approaching 1, probability is approaching 1, this one will be approaching infinity. Any question on this slide? Because you need understanding of this, the concept I just explained now. Any question concerning it? No question.
No question for now.
Okay. Okay, that's great. Now, so the people that were supposed to, if let's say we didn't even wait till 6 o'clock, they will not be here. See, somebody sent text to me that message that they have not, none of them has come. They said that they are in hold up. Now, relative risk. Let's now look at what does relative risk mean. What of odds ratio mean? This relative risk, also known as risk ratio, is comparing two risks. You know, we say risk is probability. Probability divided by probability. That's why they use it for the situation. Okay, we have two sets of people. These people smoke cigarette. These people don't smoke cigarette. What is the probability that these people that smoke cigarette, somebody that smokes cigarette, we have cancer of the lung? What is the probability that someone that does not smoke cigarette, we have cancer of the lung? So the risk, which is the probability among these people that smoke cigarette, all you need to know how many of them, how many now develop lung cancer. You have to, oh, if there are 1,000, 50 develop lung cancer, 50 over 1,000. That is the risk here. The people that don't smoke cigarettes, if one person develop lung cancer, say 1 over the 1, if there are 1,000 over 1,000, that is the risk. Comparing the two risks means that you want to divide them. Because you can compare by different ways now. You can compare by minusing one from the other one to leave one remain. Then if you decide to divide one by one, that is ratio. You know, ratio is what you get by dividing two quantities of the same unit. I often explain, I just use distance to explain. I say if somebody travel 400 kilometers in 4 hours, if you divide and say, oh, the speed is 400 kilometers divided by 4 hours, it gives you 100 kilometers per hour. That is the speed or the velocity. Because the unit, the numerator is kilometer, the denominator is hour. So the result is kilometer per hour. That is the unit of what you get. That is the speed, the unit. It's not a ratio because it has unit. But if somebody travels 400 kilometers, another person travels 4 kilometers, you now divide 400 kilometers by 4 kilometers. Both of them are kilometers. You get 100 also, but that kilometer will cancel kilometer. It will know it's a ratio, it will be unitless. You just say the answer is 100. It's 100, not 100. It's a ratio. So when you divide two things of the same unit, there are many things that are ratios. In real life, that Z score is ratio. All these Pearson, all these chi-square, you see, they are all ratio. That's why they don't have units. Pearson correlation, all of them are ratio because you don't have unit. Because you have divided two things of the same unit. So it's the same thing when you calculate risk among one group, you calculate risk among another group. You now divide risk by risk. That's ratio. That's where you get the word ratio from. Both relative risk and odds ratio, they are ratio because you get them by dividing the same two things of the same unit. That is why you can call relative risk risk ratio, ratio of risk ratio. Why they call it relative risk? What they just do is that they use it to compare the people that are exposed, the risk among the people that are exposed, by the risk among the people that are not exposed. So in this issue of lung cancer now, if you say the risk probability of lung cancer among the people that smoke is this, and I say probability of lung cancer among the people that don't smoke is this. If you want to compare, you now say you want to divide if you want to know because you are feeling that smoking may be causing lung cancer. So it will make sense for you to put the one you are calculated for smoker as the numerator and the one you are calculated for the non-smoker as the denominator, so that you want to know how large, how many times is it bigger. So you are trying to look at the risk relative among the relative to the risk compared with relatively to the risk among non-exposed. That is where the word relative comes in. So whether you call it relative risk or risk ratio is the same thing. You will see now it's the same thing applicable to odds ratio. The only difference that you can see there is the difference you see in between risk and odds. Risk probability is futuristic, but there are some situations, if something has occurred, you cannot calculate risk. For example, now, if you want to do a study, this issue of lung cancer causing, what do I call it? Smoking causing lung cancer. You are doing the study, and at the end of the day, you are doing the study, smoking causing lung cancer. And if you decide to use a design where you can recruit people that are smoking and follow them up in future to see how many will develop lung cancer. Yes, that one is risk. You are calculating, you calculate risk, because by the time of that your study, you design it, that thing has not happened. So that type of study, that's what we call core study. Experimental, they call them longitudinal. Experimental study also is like that, because when you start before you do your intervention, the thing has not, or you are looking ahead. The same thing with the core study, because the risk is futuristic. You can calculate risk now. But if it's something that somebody has developed the disease, you want to use a design like case control, where you can see somebody has the disease. You cannot calculate the risk of the person having the disease. Even the risk of exposure, you are not calculating. You can only calculate the odds of exposure. That is, wait, I know that before this person have the disease, he might have been exposed. We cannot even calculate the risk of exposure. They want to calculate the odds of exposure, because you can calculate that odds only from risk. And it is when the risk has happened, you can calculate the odds. Can you see now? That is why the logic of this odds ratio comes in. So, and you see the way we calculate odds from this. So when we go into it fully, you understand. Odds ratio is used when occurrence of an event, incident of a disease, cannot be calculated because the event had occurred in the past. So, because in observational design, where you don't do experiment, two things do happen. Sometimes when because you cannot, in disease causation, you cannot perform experiment of human being, even animal self. See, it's not ethical. Though before we were doing it, but it's not ethical. The animal also, they have that. You cannot afflict animal with disease and see, you want to see how it will go, so that you want to know how it causes disease, no one will know. So when it comes to disease causation, you cannot say you are doing experiment unless you can do experiment for prevention. Now, if you carry out a study, an observational study, like this one I just gave now, core study, maybe a particular disease that is if it's common, by the time you follow up, after some years, you may see people that develop the disease. Yeah, you do your research, analyze your result, fine. But there are some diseases that are very rare. If you start following up, people that are exposed to the agent you think or factor you think is causing the disease, you may wait for 40 years, you have not even seen one, or you don't see enough to even make any reasonable analysis. it will amount to waste of energy. And core study is the most costly, more costly than experimental design because of that follow-up for long. So the intelligent people come, okay, if the disease is real like that, why should you use that method to be wasting money and wasting, you not even get anything? If the disease is real, if you cannot have few that have the disease, look for them from different centers, from different states, even different, even country also. Look for them and use them to do a study. You have already developed, you are not the one that caused it. You now, that is where the case control comes in. In that, you get the cases, that's okay. I want to ask them questions about what they are exposed to and resorted to this disease. In this case now, even the exposure, you are not calculating the risk, you are calculating the cause of the exposure. What is it? Is it probably that this person was exposed to this agent, this factor that made the person develop disease? In that situation, you cannot calculate risk of the disease because the disease has already occurred. You can only calculate odds. And that is why in such study like case control study, even cross-sectional study, you calculate odds. You cannot calculate risk. Does it make sense? But however, in cases where you can calculate risk, you can still calculate odds. After all, you calculate odds from risk. Even in experimental study, in core study, you can calculate odds ratio, you can calculate odds. Many people think that you cannot calculate it. They say risk odds ratio is for risk control, while relative risk for no. The only thing that relatively can never feature in case control and cross-sectional design. Because in case control, of course, we know that the disease, we have the cases. In cross-sectional design, you just go. Some of them you are studying, some of them have the disease. And they also have the factor together at the same time you met, because you just look at it together. Just like we say obesity and hypertension. So you see there's some of them are obese, some of them are hypertensive. You don't even know which one comes first. Whether the obesity comes before hypertension or hypertension comes before obesity for each of them, you don't know. That's why that's one of the drawbacks of a cross-sectional study, because you cannot establish temporal sequence. The meaning of temporal sequence is that the exposure, you can establish that it occurred before the disease. Because there's no way someone can have the disease from an exposure if the exposure has not occurred. If somebody has disease before the exposure, you cannot say it's the exposure. That is not an exposure to disease. So what is causing something must have happened before it caused something. So in cross-sectional study, you cannot say it. You don't know. You just see that some of them are obese, some of them are hypertensive. For each of them, so some people are obese before hypertension. From some of them, some of them were hypertensive before obesity. So you cannot establish that temporal sequence with cross-sectional study. So in that case, some of them have the disease. That's why in cross-sectional study, case control study, you can't talk about relative risk. It's not possible. Then you can talk about odds ratio in any study, even including experimental, including core study. You don't know that. Okay, when you run, you want to do some analysis, logistic regression, which irrespective of the type of study you are doing, the statistic for it is odds ratio. We told you cannot calculate odds ratio. But there's a way also you can convert odds ratio to relative risk. So, example, case control study, that's then cross-sectional analytical study, that's where you use odds ratio. Most of the time. Most statistical methods such as logistic regression that are employed to identify the predictors of outcome and also remove confounders use odds ratio to measure the strength of association. So odds ratio, relative risk and odds ratio. You know, I think I just want you to have some, just to look at this picture to explain further the study type and show more light on what I just said. how they are related to calculation of risk and odds, eventually odds ratio and relative risk. Risk can be calculated only from the data captured when the event has not occurred. Yes, I mean, now you can only calculate risk when the event has not occurred. That you know, when you start your study, the event has not occurred. You can calculate it. Look at this line where they are hanging. Look at this line in the middle. In a situation, look at case control now. Cases, compare risk and frequency. This one they are looking back, they call it retrospective. There is a two type of cohort here, retrospective cohort. The cohort just mean a group of people that are, maybe they are doing the same thing. It is a word borrowed from Roman Empire, from the Roman military in those days. A cohort is a group of people that join military at the same time. Then they are cohort. They join at the same time, they are progressing at the same time, they are likely to retire at the same time. They are cohort, not like mate. It's just like in medical school or in school. Your cohort, you join school together and you come out together and say yourself, you are cohort. So cohort means, okay, maybe these people are smoking at the same time, they're smoking, you just gather them. They are exposed to a factor around the same time. They are cohort. You now follow them up to the future to see how many of them will develop the disease. There are two perspectives to it. So look at it now. When we look at the data we collected, we want to see at the point that we start the study, as the outcome occur or as it not occur. That time you are doing your study, if the outcome has occurred, that shows that you cannot calculate the disease or outcome has occurred. You cannot calculate risk. So that's the example of case control and cross-sectional study. But if the outcome has not occurred, that shows that it's not the outcome you are looking at now. You are looking at the risk factor. Those are the things that can be representing what we are talking about. Who are those who are exposed? You now follow them up. How many will develop the outcome? But in the case control, you are seeing the outcome with your eyes. You want started asking them, were you exposed to this risk before you have this? Were you exposed? For example, now, if you say that can OCP, oral contraceptive pill, cause varicosity of vein, varicose vein. Now, if the people you are dealing with, they have developed varicose vein, you recruit them together. You also have some control that they are similar in all respect, but they don't have varicose vein. The women, they are similar, but they don't have varicose vein. So that's what is called case control. You begin to not ask the same question from both of them. If they have ever used OCP, if they have used how often, they'll say many things. For how long? You ask them the question to listen. If more of the people that have developed the disease, they actually were exposed to OCP. If OCP was responsible for their problem, more of the people that developed the disease would have been exposed to it. But of course, you're going to see somebody that developed the disease, never had any contact with OCP. But if the OCP is secreted, more of the people that have the disease will report that they have one day way or the other taking OCP, even the dosage they will have taken for a longer period of time. Now, if the disease has not occurred, so you don't have anybody sick, what you can say is that, okay, maybe there is not a matter of you have not seen anybody the OCP, you are starting with, okay, how many of you are taking OCP? There's no varicose vein now. You are not seeing patients with varicose vein. You are saying, okay, how many? You are now looking at the people that are taking OCP. You want to follow them up in future. How many will develop? Now, They call the cohort study prospective because you look into the future. They call case control retrospective. You are looking back. But the word has been discarded because you can have retrospective cohort. For example, the retrospective cohort you are seeing here is common now in industrial research, occupational research, health research, where maybe people work, are exposed to some factors in the environment some years ago, maybe 30 years ago. And after 20 years, 10 years ago, they developed the disease. You can get to the record. You know, in a company, how many, who are those that were exposed from 30 years back, in 10 years back now, which is 20 years different. You look at the record, how some of them have developed certain disease. So if you analyze it like that, it's a cohort study in the sense that you are starting with, they were exposed in the past, and the disease also occur in the past later. But of course, the exposure is more past. But it's retrospective because both the data, both the exposure and the outcome you are measuring the disease, you are looking backward to capture them. That's why it is still a cohort study, but it's a retrospective cohort. We also have nested case control inside a cohort study. For example, now, imagine if you follow up some people after you have finished the study, you can start, within that study, you can keep that select some people also that have the, you mingle together, either the cohort and the control. You now select all the people that have the disease, whether they were in cohort or they were in control. You now begin to look back again. That is what called nested case control. It is nested in the data that have been collected for cohort study. So let us talk much about that, because so that the thing will not talk to epidemiology class, because some people may not be interested in all those. Now, any question from what I've just discussed that we can see? Any question? Any question? Are you with me?
No question.
Hope you are not taking tea. Now, let's look at comparing risk and odds. In comparing risk and odds using 2x2 contingency table. Occurrence of events are as a result of exposure to certain factors. When something happens, it's because you are exposed to something that makes that thing happen. If somebody gets sick, there must be something that has happened. The person may not know that might have happened in the past that resulted to the disease. If you have certain problem, another person does not have that problem, there must be something that happened to you in the past that did not happen to this other person. That's what makes the difference. So the relationship between exposure to a factor and the occurrence of an event can be depicted in a 2x2 contingency table. So what I'm saying now, if something happened to somebody is sick, and there's a factor, something that might have occurred in the past that might have resulted, how do you give a mental picture or create a mental picture of relationship between the exposure, what happened in the past, and the problem the person is having, the disease? You can do that through a 2x2 contingency table. The 2x2 contingency, what it does, you know, we have already talked about that's cross tabulation contingency, but this one is 2x2. Now, when you are doing it, it is conventional to make the exposure horizontal and the outcome vertical. Can you see exposure status? Exposed, not exposed. So in 2 by 2 that shows that the exposure will have 2 categories. It's either there exposed or immersed. So the outcome event we have 2 categories: event occur or not, sick or not sick. Just like smoke or did not smoke. Lung cancer, no lung cancer. It's like that. So when you do it like that, it gives you. That's why the A, B, C, D is conventional. These are the address. They call the first cell A, the second B, the other one C, and D. Now, me, I prefer using example rather than giving you this formula now. This is the formula for relative risk and this formula for odds ratio. I prefer an example, a good example. Look at the example here now. In a study of 500 smokers, 500 smokers and 1,000 non-smokers were followed up for 10 years to see how many will develop lung cancer. This is a case of cohort study because we are starting with smokers and non-smokers. It's later you are seeing if they develop lung cancer. So it's a cohort study. If 25% of the smokers and 2% of, not percent. If 25 of the smokers and 5 of the non-smokers develop lung cancer, respectively, what is the relative risk of developing lung cancer following smoking? What we are seeing here is that if, look at the table, the thing is just snapshot. Smoking, total that smoke is 500. Can you see at the extreme end? Out of each, yes, the lung cancer vertical. Yes, for lung cancer means they have lung cancer is 25. The remaining 475 didn't develop lung cancer. You also have 1,000 people that did not smoke, and only 5 developed lung cancer. 995 developed lung cancer. So how do you, what do you mean by this? How do you, instead of you to even say, hey, well, what is relative risk? Just look at it. What is the risk among them first? What is the risk of lung cancer among smokers? What is the risk of lung cancer among non-smokers? When you have calculated, you now compare it by dividing the risk among smokers by the risk among non-smokers. That is the relative risk. And see how many times the risk among smokers is higher. Whereas when you divide it by it, that will be able to how many that is it bigger than the other one, and the risk among non-smokers. So now, if you look at it, the risk among smokers will be what? Let's speak to it. Let somebody talk. What is the risk among smokers now from the table? How will you compute it? The risk among smokers. Not somebody talk. Nobody is answering.
Is the risk is the total number of those that smoke over total number of those that smoke and did not smoke that develop a lung. I mean, what do I want to say? The total number of those people that smoke and develop cancer over total number of those people that smoke, whether they develop cancer or not.
Yeah, that is on this table now is what over what now?
That is 25 over 500.
Yes. So the total number of people that develop cancer over the total number of people in that category that smoke, because among them that develop lung cancer. So that shows that even the 25 is part of the 500.
Yes.
Yeah, 25 over 500 is the risk of lung cancer among smokers. For among non-smokers, what is the risk of lung cancer now?
That is among those that do not smoke, the total number that develop cancer from that, which is 5, over total number of those that do not smoke, which is 5 over 1,000.
Yes, 5 over 1,000. Can you see that? Simple. So if you want to say relative risk now, we'll now say that your 25 over 500 divided by 5 over 1,000. That is relative risk. Because you are trying to divide the first risk by the second risk. You are dividing this risk among the smoker over the risk around not smoker. That was here, 25 over 500 over everything over 5 over 1,000. When you change your subject or formula and you change the times, this one could it will give you this 10. What 10 means is that relative risk is 10. That is, the people that smoke, the risk of developing that lung cancer you have calculated is 10 times bigger than the risk among the non-smoker. Okay, so it will give impression, wait, like this smoking is contributing to lung cancer. Very simple. That's what brought this one. Can you see? In the cell, if you remember, that 25 is the A. 475 is B. 500 will be A plus B. Then for this one, 5 will be C. 995 will be D. Then 1,000 will be C plus D. So the risk among this will be A, this 25 over 500, which is A over A plus B. Can you see? Why the risk among the non-smoker will be this 5, which is C over 1,000, which is C plus D. Can you see? That's why the formula for relative risk is like that. Very simple. Then also calculate the odd ratio. If you want to calculate the odd ratio for the same thing, don't worry, we'll explain with another example. Though you can calculate the odd ratio out. We'll explain with another example before we go around. Should we run the relative risk first? Let's run it. Let's run the relative risk. There is a data set there. Smoking lung cancer. Smoking lung cancer. Is it smoking or smoke lung cancer? Smoke lung cancer. Somebody should read it and share with us. Somebody should, it's one of the files I sent to you. Smoke lung cancer. Smoke lung cancer. It's different from lung cancer smoke. There's one lung cancer smoke lung cancer. Who is sharing? Dr. Lamingo, you went out for some time. Yeah. Yeah. So you just go, we are dealing with proportion. It's still cross-tabulation. Just go to analyze. You can see, okay, wait. You see, look, before you do that, let's look at the data set. You see smoking, you see lung cancer. Just forget all those logistics, me that created those one later. The original video is smoking and lung cancer. So if you go to the view now, go to see yes or no. 1 is yes, 2 is no. If you go and check, if you can share the way we put it. The same thing with lung cancer. Yes, 1 yes, 2 no. The same thing with smoking, same thing with lung cancer. That's great. Let's go. It's okay. Let's go to analyze now. Descriptive statistics and cross-tab. So which one go to the row?
Smoking.
Smoking, yes. That's the exposure. The column will be lung cancer. Now go to statistics. You see risk. Look at risk. Click continue. Click OK. So stop sharing and share the results. Share the results. Okay. You see, so go down. So that table is the same thing you have seen before. It's not the table. So we are going straight to the results. You see that, the computer is garbage in, garbage out. It will calculate the odd ratio for you. Because in case that's what you want to use the data for. Then the relative risk is that number one, for cohort lung cancer is equal to yes. It tries to tell you that, okay, for the people that have lung cancer is equal to yes. Because that is the outcome of interest. So if you look at it, that's 10, you calculated. That's what we calculated. The relative risk is 10. But it gives you confidence interval. Though for putting the confidence interval, you don't need to even stress yourself on the computation. But look at it. The confidence interval is from when to when. You see the confidence interval. Let me now see how explain how you interpret confidence. You can stop sharing. Let me share my slide and talk about how we interpret confidence interval. Very, very important. Or maybe before that one, let's because it's the same thing. Let's continue. Let's explain. Let's talk about the example for odd ratio also, so that we'll go and run it also. Before I will come back to explain, because the confidence interval, the interpretation is the same. Before we talk about interpreting confidence interval. Look at the example here. This example we want to use for the relative odd ratio. This is a case control study. Of 200 patients treated in a hospital, 50 have lung cancer. Of these patients, 45 are smokers. Of the remaining 150 patients, 60 are smokers. What is the odd ratio for smoking? You look at it now, 200 patients, 50 have lung cancer, 150 do not have lung cancer. So the cases are 50, the control are 150. Out of the 50 that have the lung cancer, 45 smoke were smokers. Out of the remaining 150, the control 150, 16 were smokers. So what is the odd ratio for smoking? Also, you can calculate the relative risk from it. But look at this one. Look somehow to explain it, because people just come, but you can actually look at it from a perspective. Let me see if to work it out. Now, if you want to do this one now, you may have to say, okay, look at that table. Lung cancer 50, control 150, no lung cancer. Here now, the horde of smoking you are looking for is not lung or lung cancer. So for you to calculate the horde of smoking for each group, you must understand the way to calculate the risk of smoking, which is probability. Horde is risk over 1 minus risk. So what is the probability that somebody smoke among the lung cancer people? What's the probability that somebody smoke? Let's look at it together from this. You don't know, just tell me something over something. That's all.
That is 45 over 60.
Yes, thank you. Because out of the 50 that have lung cancer, 45 smoke. So 45 over 50 is the probability risk that somebody smoke. What is the risk that somebody did not smoke?
That is 5 over 60.
5 over, is it 60 or 50? 50.
It's 60.
No, I don't know what
No, 60 over 5, I said. No, I'm okay. It's 60.
45, the first one.
It's
Among
45.
how many people have cancer, lung cancer?
45. 45 that has cancer that does not smoke. I mean that smoke. Then those that does not smoke, but those that don't have cancer and smoke is 60. It's not 50.
Leave that one. Forget about people that don't have cancer. We are dealing with people that have cancer now. The 50 that have cancer, what is the risk that they smoke? Is it 45 over 50? Is that also?
Yeah, people that have cancer is is 5. Yes.
Yes, people that have cancer, 50.
Yes.
The risk that they smoke is 45 over 50.
Yes, yes.
The risk that they did not smoke is what?
5 over 50.
Thank you. Now, what is the odds now? Because you have calculated the risk to be 45 over 50. You know the odds, it will be risk over 1 minus risk.
Yes.
The 1 minus risk there is 5 over 50. The risk is 45 over 50. The 1 minus risk is 5 over 50. Do you get it now? Okay. So the odds of smoking will be 45 over 50 divided by 5 over 50. Okay. When you change it, change of this problem, you know what it will become? Maybe let me just use my this to write it here now. You'll be looking at it. Look at what I'm saying. Let me write on the screen. 45 over 50 is the risk of smoking among the lung cancer people.
Yes.
You now say divided by everything, or you just put it here, divided by the risk of not smoking is 5 over 50. Abi?
Yes. And
this is the odds now. Odds is risk all over 1 minus risk. The risk is 45. The risk is 45 over 50. 1 minus risk is 5 over 50. So the odds is 45 over 50 divided by 5 over 50. Do you understand?
Yes.
If you have gotten this concept of odds, so it's the same thing as saying 45 over 50 times 50 over 5. Abi?
Yes.
When you are changing division to times, this one cancel this one like this, It remains 45 over 5. So that said, the odds of smoking is we can just say A, because this 45 is A, this one is C. Can you see A over C? Do you get it now?
Yes.
Now, when you now come to the same thing, what is the odds of smoking among the people that don't have lung cancer is 60 over 90.
90.
Do you understand now?
Yeah.
So the odds ratio, that is the odds of smoking among the lung cancer people divided by the odds of smoking among the non-lung cancer people, can you see now? It will now be this one divided by, can you see, this is the odds for the lung cancer now, 44 over 50 over 5. The other one over for non-lung cancer is 60 over 90. So if you see follow the change of surgery of this thing, blood mass also, 45 over 5 times 90 over 60. If you look at it, this table now, 45 is A, 90 is D, 5 is C, and 60 is B. That is why they will say A,
D,
D over BC. You understand me now? A short way, just say the whole ratio, look at that cell, just cross it. AD over BC. Do you get the picture now? If you do it now, you're going to get something like 30.5. That is the answer. 30.5. Because if you call this one out, this one, this is 9, Abby. This one, this is 3, let's say 2. 3 goes here 20, 3 goes here 3. 3 in 20. So if you actually, this 20, this one, cancel this one, 9 times 3 times 7 all over 2, make it 30.5. 30.5, right? Then 7 over 2, 30.5. The answer will be 30.5. So the Hort ratio is 30.5. So let's run it also. So you can share again. This one now is lung cancer smoke. Defined as a lung cancer smoke. It's not smoking lung cancer. The second part, lung cancer smoke. When you do that, there's a lot of things to still learn in this thing. But once it's time, we'll stop. So that by tomorrow we'll continue because we're not many today. So there's no much question that draws back. That's why we're able to move faster. But if you won't start discussing tomorrow's work, there's no problem. By tomorrow, you get to know some other things hidden under this thing. Is your desktop you are sharing with us? Though you can go to where it is sharp and just if you know where you saw it, just double click it will open. Where you store the file. Lung cancer smoke. Yes, that's it. So just without wasting time, just go to analyze, cross tab, and go to cross tab. Yeah. Oh, Ben, you are following Dr. Lamingo. Are we together?
I'm okay.
Yes, we are.
Why did you come late? Both of you even come after it's around 7 that you people came. What happened? Thank God that we even started early because if we have started early also, it would have been amounted to the same thing because many people, even by 6, they were not here. Yes. So smoke will be is the exposure now. Smoke will be
column.
No, lung cancer is the column.
Lung cancer is the column.
Yes. Smoke is still the exposure, even though the lung cancer came before this, but the smoking is still the exposure. Lung cancer is the column, yes. No, it's not smoke logistic. Remove that. It's smoke, not slow logistic. Those ones I just coded. It's not the one who have logistic. Ordinary smoke and ordinary lung cancer. Okay, remove that. Yes. Then the lung cancer. So statistics, risk. No, both of them are measure of risk also. Why odds is a proxy to risk? Yes, I'm now. It's risk, okay. Odds is like acting risk. Continue. Okay. So enlarge is something, we can see your result to enlarge it, yes. Can you see the odd ratio? 30.5. Can you see?
Yes.
Yeah. Let's stop here. Tomorrow, the confidence interval aspect of it will continue with it and some other Good to see there is some other revelation around this thing. All this audio show and relatively, we're going to see some revelation tomorrow. So let's stop here. This 6 minutes to 8. I spent 3 hours. Any question on what you have done?
No, I'm okay.
Ben, Dr. Lamingo, any question? I'm not hearing anything.
I say I'm okay, me or most.
Only you, I'm talking of other people, I'm calling them.
Okay.
Maybe they are not even there.
Dr. Lamingo. It's better we continue tomorrow.
Yes, we'll continue tomorrow. Okay, thank you.
Thank you.
And Ben, maybe they are not more. If you're not, don't unmute yourself, we cannot hear you now. If you are talking, you have to unmute. Lamingo, Ben, they are not there.
Good night, sir.
Good night, thank you.